Okay, hello students. When I left you in the last video, we started a run of the season 137 on the scintillation counter, and it's been running for a while, so I thought this isn't the goal of this video, but I just thought I'd show you what happens after it's been running for about, you see the real time there is about 1500 seconds. The live time is about a little bit less, about 1400 seconds or so. And the difference, of course, is real time is the actual real clock wall time that it's been running for. And the live time is the time that collections happen, because every time a collection comes in, the computer has to do a bit of processing on the data point that came in. And so it loses a little bit of time in that processing mode relative to the live clock time. So that's why those numbers are a bit different. We can see that we've had over 2 million counts coming in. So if you added up all of these channel counts that you have, you get a number well over 2,600,000 some on. So there you go. And I'd just like to show you what gamma ray spectroscopy is about. It's very fun, but you can see once again the very dominant peak here, often called the photo peak for a monoenergetic emitter like cesium 137. A definite absence of any gamma rays in here. A little bit of a bump right there, and look at how well developed this bump here has also become in this region. Then it flattens out once again, and of course a huge spike over there. All this needs to be explained, say, in a lab report. But what I wanted to do in this video then is I wanted to show you a little bit more about how the amplifier interacts with all this and get us ready to take the data that's needed for our experiment here. Okay, and so all this we've been doing so far is just a warm up. So go ahead and clear that out. As nice as it was, we'll just clear it out. Get the scale, of course, sort of down here on some smaller numbers here. And so here's what I'm going to do. I'm going to start the spectrum up here, and I'll just go ahead and do that now then, I guess, just to sort of see the cesium photo peak rising again. So there it is. So you see it's rising right about this region right here. And now what I'm going to do is I'm going to change the amplifier gain. So I'm going to reach down here onto the amplifier right about here, and I'm going to turn the gain down some. Okay, I'm going to turn it. Let's see if we can maybe get both even in the same screen. Yeah, well, maybe we can do something like this. Something like this might work, okay? Well, it looks like the screen's a little bit small. Let me just zoom it up more. So I'm going to turn the amplifier gain down, and let's watch what happens. So here we go. I'm going to give it a good swing down, like that. And so what you're seeing now is that the photo peak no longer is growing in this region right here. It's growing over here. Why would that be? Well, I've turned the amplifier gain down, and so on sort of as a whole, the voltage that are coming into the MCA to be thrown in one of these channels here is smaller. All the voltages are smaller, so the photo peak is going to shift over. This is not a property of cesium 137. There hasn't been any big physics that went on in there at the moment to cause the peak to shift. I just turned the amplifier gain down. Let me turn down even more. So I've turned the fine knob down, the fine gain knob down just as much as I can, and so there's the photo peak rising there now because I've made the voltages still lower. Let me turn it up even more. Turn up there. See, there's about where it used to be before. And turn it up so it sort of appears. There we go. There we go. Look where it's appearing now. So it's appearing almost at the edge of the highest channel. So clearly I'm approaching 10 volts with that maximum gamma ray energy. And if I even go down and look at the oscilloscope screen, I see indeed that these pulses are all nice and high here. And I'm seeing a lot of that saturation at the top, which I do want to avoid. But by and large, most of them still are in that 10 volt envelope right there. And so there's all the peaks. And so let me turn maybe the coarse gain knob down. So remember, there's two knobs on the amplifier right here. There's the fine gain right here and the coarse gain right here. So the fine gain is sort of up, putting that peak where it is now. I'm going to turn the coarse gain down from 50 to 20 all the way down and see what we get. Yeah, look, and so you see like the photo peak from season 137 rising way over there. So the point for telling you this then is what I've done by changing the amplifier knobs is I've changed the overall level of all the voltages going into the MCA. I'm making them smaller than bigger, and so in fact if I even clear it here, what I can actually do is even compress a whole cesium 137 from taking up the whole screen to taking up just a little bit of half over there. So you'll see sort of the same spectrum that we started with, the one that was running for a while there, but now it's all just sort of compressed, all nice and cute in this third of the screen over there. Let me tell you why this is important for us and what we're going to do. Because we have several gamma ray sources that we're going to run through the system, and what we're aiming to do is get these channels calibrated into energy. That's a big outcome of this lab here for you to do that. So to produce a graph of, say, a cesium 130 cesium-137 spectrum, where this x-axis is not in channels, but in energy, a good physical parameter like energy, like we'd literally like to read on this a graph, say like this. Now we don't want to read 384, channel 384. We'd like to see the number 663 appear right below the cesium photopeak, because that's the energy that cesium-137 emits at. And if we ran something else in there like cobalt that has a couple of peaks in it, we'd like to see those peaks labeled as well. And so what we're going to do then in the next video is we're going to run through a bunch of different sources and see exactly where those photo peaks fall. Okay, so what I'm going to do at the moment here is I'm going to sort of take the cesium off the detector. So remember, I had the cesium disc up here, so here it is. I'm taking it off the detector, and I'm going to put, let's well, hold on a second. Does the spectrum sort of stop on the screen? Oh, yes, it does. This Windows O is right in the middle of the action. It stopped because the source is gone. And now what I'm going to do is I'm going to put cobalt 60 up there. So I just put the disc cobalt 60 on the top of the detector right here. Let's go look back at the screen now. Everything's still running. Let's see what we're going to get. So, of course, the cesium is no longer there, so this action kind of is stopped. But now we're seeing some new peaks come up over here. Let me just zoom in on them a bit there. Of course, the cesium spectrum is well developed, is running for a while. But now we see the cobalt 60 coming in. Look at that. There's 2 peaks for cobalt 60. So 2 peaks means that cobalt 60 actually emits two gamma rays. And would you say gamma rays are the same energy, different energy? Well, different energy there, because there's one's going to have this energy and one's going to have that energy. And it turns out that cobalt 60 is the highest gamma ray energy emitter we have in the kit. So if I recall, I told you that the cesium photo peak, cesium emits at about 663 keV, where cobalt 60, this highest one here, is over 1,000 keV. In fact, it's 1,333 kilo electron volts, or if you wanted to change units, 1.3 MeVs. And this one right here is 1.1 MeV. So the point of the amplifier gain is, as we move on to the next video, we're going to like to collect a whole bunch of sources here with a common channel consistency among them all. Like we always like to expand these spectra to fill the whole display, but we don't want to change the amplifier setting and put cesium's photopeak over here for cesium, because then that's going to knock cobalt's photopeak well off the screen. Like if this cesium photopeak, say, was right here the way we had it earlier, then these 2 peaks for cobalt would be way over here off the screen, and we don't want to do that. Get my focus back here. We don't want to do that. So since we know cobalt is the highest gamma ray energy emitter, we're going to tweak the amplifier settings to put these photopeaks right here in this area of the screen, and everything else that we put on the detector, all the other sources like the barium and the sodium-22 and all of those, are going to have their peaks fit in some of these lower energy channels. So we'll have a nice consistent channel set among all of our sources. Then we can get in and start talking about calibrating the x-axis.